All right, so we'll move on to our last presentation from Oregon State. Dr. Turkan will be here to present it. The title is Toward Automation and Crack Detection and Measurements, Benchmarking of CNN-Based Algorithms.
Let's see. Okay. Hi, everyone. My name is Yelda Turkan from Oregon State University. I know I'm between you and the lunch break, so I'll be quick. So I'm presenting this on behalf of my PhD student, Donghoon, who could not be here today. And we're changing gears a little bit. This presentation is not exactly about, construction, engineering, or management. We are using crack detection and measurements, image-based crack detection and measurement to automatically identify cracks from images so that the structural engineers can later use this to assess the condition of the structure. In the United States, we have many bridges that are structurally deficient or needing repair and preservation. Approximately 37% of the bridges in the United States, they require repair and preservation, and roughly 7.5% of them are categorized as structurally deficient by the ASCE, American Society of Civil Engineers. Also, one of the other motivations for us to do this research is in the Pacific Northwest of the United States, we're in an earthquake zone. We have the Cascadia subduction zone. In the case of an earthquake, in the aftermath during the reconnaissance events, if you can capture the structural condition using automated image-based techniques, this would really help further on for the structural engineers to quickly have access to that data and then improve their decision making and the amount of time they need to do that. So there are several image-based techniques. Several researchers have been working on this for the past 2-3 decades. There are the image morphological operations that are traditional approaches, but there are also deep learning-based, CNN-based methods that are out there to detect the cracks. So in this work, we used. Our goal was to benchmark our algorithms first using data from that we collected from a laboratory experiment, and then later on we would like to apply our algorithms on a data set that are collected actually from a bridge and other larger structures. So to detect the crack, we combined two approaches. CNN-based methods are less sensitive to the, they can capture more of the details, and the image morphological operations are less sensitive to the changes in the contrast in the image. And for measuring the crack, the length and the width of the crack, we use skeletization and orthogonal projection methods. This is the overall methodology of our overall methodology in this research. So we first pre-process the data using manual filtering and grayscale conversion. So this deep crack method we used, it is previously trained using roughly 3,000 images. So we applied that algorithm on our image on the images we collected from the experiments that was collected in the lab, and then simultaneously we also applied the morphological operation and then combined the two results. As you see here, the deep crack method was able to get the more of the details from the crack. And then we combine the results. We were able to get the boundary of the crack that way. For the crack measurement, once we got the boundary of the crack, we applied a skeletization method. And then after we applied the skeletization method, as you see, there are a bunch of branches. This is the crack itself, right? We applied a branch filtering operation, also called pruning. And then in the next step, we measure the length of the skeleton to get the crack length, and then to measure the width of the crack, we apply the orthogonal projection, and then measure the width of the crack in several locations, and then compare that to the actual branch or actual crack width. These are the shear tests that was applied at the University of Washington that my colleague Paolo Calvi did. They were done. These are ultra high performance concrete. Specimens are about 90 by 90 centimeters with a 7 centimeters depth. As you see, there are 3 different specimens. What we did was to extract the region of interest. We manually cropped the images to get the part that has the crack itself. And then these are just some of the definitions. The crack, when we say crack skeleton, is the 1 pixel wide line representing the orientation of the crack length, is as you see here. And then we got the crack orientation, and we use the perpendicular distance between the in the crack to measure the crack width. Here you see the results that we obtained using the deep crack and the morphological image processing. As you can see, we were able to get most of the details of the crack. I don't know if you can see these, but these are like just the numbers the structural engineers put when they do the crack shear tests here. We were able to even get those here that we didn't need. But so these are the crack detection results. Some of the details we weren't able to capture. They are like we lost some of the details, but those are super important. The average width of those cracks were less than a millimeter. It's about, average was 0.76 millimeter. So from the sense of like the structural engineers don't really, that's not a crack that would affect the structure itself, or its yeah. So and then couple of things. The branch filtering is good, but we lost some of the details, the length of the detail. So the pixels we lost at the edges because of the filtering. So that's roughly about 3% among 3 images that we lost the detail. And these are our results on the length. So this is the result that we obtained using our proposed method, the ground truth results. As you see, the rough average accuracy is about 92%. So the ground truth we manually measured on the image. We just manually measured the crack length. So based on the previous studies, the average accuracy was about 95%, and we believe that we can further improve our results by fine-tuning the branch filtering algorithm. Next, we looked at the width measurements. As you see here, the average width, average accuracy obtained was about 90%, which aligns with similar to the previous studies that they obtained. For the width measurements, we randomly picked 5 checkpoints I think in reality, that's how structural engineers do it anyway. They just look at, to measure the width of the crack, they go through and randomly pick different points and they average it. So we were satisfied with that. Again, as you said, right now we are working on adding more data that we collected from a laboratory environment and with more images. And the next step will be to use drone captured images, which will be more difficult because of the shadow effects and things like that. We also, so this is a structure, it's in Japan called the E-Defense Center. This is like a 3-story building. It's like a shake table. They do the tests, and then the structural engineers later manually measure all the cracks in the building, and then they use it for structural analysis. So my colleague Paolo actually collected a whole bunch of 3D point clouds from that building, and they're trying to manually extract the cracks from the laser scan. So we're also going to look into if we can use this approach on the LiDAR point cloud. That's going to be our next step after the image recognition. And with that, thank you. If there are any questions, I'm happy to answer.
From the samples you show, the images seem to be quite high resolution. Do you see this being just as effective if say the drone images are taken from further back and the resolution isn't as high?
That's a good question. No, yeah, so for that, the drone flight planning is very important. There are methods that you, when you're planning your drone flight, you first take a whole bunch of images, and if you see there are some like cracks or other like a spelling, it's better to take images closer so the resolution is higher. Otherwise, this method wouldn't really work that well. Thanks, Thomas.
Thank you very much for your interesting presentation. I'd like to ask your opinion on my suggestion that I'm about to make now. When it comes to crack detection research, I have my own difficulty in evaluating new studies. There are many studies that are focusing on crack detection in the construction industry, but it's not easy to understand what is really working and what is not really working. So what I have been thinking about is we should propose something like MS COCO data set, the construction version of it. So when we have this good benchmark data set, then we can finally objectively and quantitatively evaluate each way of detecting crack. Then that may give us a better understanding of what works the best. What's your view on this suggestion?
Yeah, that's a great suggestion, especially for the CNN-based approach. We really need a lot of data. That deep crack algorithm we used, it was trained with 3,000 images. But as you know, any AI or deep learning method works. You get better results if you have a larger data set. So that is very important. I think the other important thing is that is working with structural engineers. They are the subject matter experts, right? Like I show you, we lost some of the details in the cracks, but they are not necessarily that important. So when it comes to that, I guess it is also important to work with those people and, not get into, get stuck in the details, and maybe the approach we, propose is good enough for their purpose and things like that. Yeah. Great suggestion. Thank you. Yes. Um, Oh, it's coming.
Okay, thank you so much. I have a question. Have you ever applied this accreditation during a rapid structure assessment? What I mean to say is the accreditation is higher during this type of analysis?
Sorry, I didn't quite. How do I apply the skeletonization?
Yes, got it. During a structural analysis.
Well, that's a good question, and my student would be able to answer that. He used MATLAB, so I applied the skeletizations on the image. After he got the crack data, he using another algorithm. He used MATLAB to do that.
Okay, got it. Thank you.
Yeah. Mhm. All right, thank you. Well, enjoy the lunch.
Thank you very much for this great presentation.